into the computer, and you should have the. So let me just introduce this session. I am Laura Barberos-Witalski. I am part of the adjunct faculty at the Center for Applied Imagination. I've been teaching for a long time as an adjunct, and I'm also an alumna, of course, of the Master of Science in Creativity and Change Leadership. I have the privilege to host today and moderate the session of my colleague, Dr. Melody Oziaprak from Buffalo State University, and Bartu Bingol from Arizona State University. And it's a very intriguing session for me. It's about creativity and mathematics, and I really am creative and flexible thinking. Let me just introduce to you very briefly Dr. Ozaprak and our colleague Bartu Bingol. Okay, so Dr. Ozaprak, Melody Ozaprak is an assistant professor at Buffalo State University, specializing in creativity and creativity education with a focus on domain-specific creativity in mathematics education. So we have the expert here. Her research examines how creativity techniques and creative conditions support the development of individuals' creative potential. In Turkey, she contributed to developing the country's first official creativity and thinking skill programs and design mathematics curricula for gifted students centered on creativity. And she also served as associate director in the research department at Johns Hopkins University, where she conducted research on creativity, talent development, and equity in education. So Dr. Oziaprak teaches courses on creativity, critical thinking, gifted education, and authors several chapters on creativity and curriculum development. In other words, Dr. Oziaprak is our mathematics and creativity star, and many more, and much more. Okay, Bartu Bingol is an assistant teaching professor of mathematics at Arizona State University. His research spans number theory, mathematical creativity, and mathematical instruction. He holds a PhD in mathematics from UMass Amherst, and is passionate about making mathematics a deeply human and communicative experience. I really hope so. As I said, I got a love and hate of mathematics here. And I give the floor to the two of you, and please go ahead and welcome to the session.
Thank you. So we are delightful to be here with you to play a well-known game with a not known at all way. So it's going to be an adventure for every one of us. And then Bart is going to take the lead to start the game. But we appreciate if you have the chance, if you could turn on your videos and join us, because we're expecting it to be an interactive experience for all of us, so that we can make sense of our experience and we can talk about math creativity in depth. Bartu, over you.
All right. Thank you very much. So thanks a lot for the introduction to Laura and also to Melody as well. So today we'll be, as Melody said, playing a game that we all know in a very unknown way. So without further ado, let's quickly get started. Let's start with this game. So everybody knows this game, tic-tac-toe. We have two players taking turns, and one plays X and the other plays O. And the strategy, the aim is to get three in a row to win the game. So to get three in a row in this tic-tac-toe map, we can use the rows, columns, or diagonals. All of them will count. So, well, let's get ourselves familiar with this game. We need a volunteer to play this game against me. Who would want to play against me? The game tic-tac-toe. If someone can raise their hand or just unmute themselves.
Volunteer.
All right. I see Amber who wants to play. Okay. So Amber, thank you very much for joining us, for volunteering us for our tic-tac-toe. So let's get started. So would you mind if I start?
I would prefer to start, but you could go first.
You would prefer to start? Sure, why not? Go ahead and start, Amber. Would you like to place X or O?
I'll do X, and then I'll do the bottom left corner.
Bottom left corner. Okay, so you are placing X here, and I am placing O here.
Okay.
Where would you like to place your X?
I'll place another X in the top No, the bottom right corner.
Bottom right corner. Here.
Yes.
Okay. So I see that you're trying to make 3 in a row here. So I'll place my O here.
Okay. And I'll place the X above the O you just placed.
Okay. And then now I will place my O here.
Okay. I'll place my X above the top right X.
This one, okay.
Mm-hmm.
So I'll place my O here, and this is the only place that you can place your X. So neither of us got this 3 in a row, so it was a draw. Okay,
Yeah.
nice. Fair. Thank you, Amber. So who else wants to play? Anyone else who would like to play tic-tac-toe against me?
Michelle, I think you are muted. We don't hear you. If you are willing to play, we appreciate it.
Oh, I see Clara raising their hand.
Yes,
Yes,
I
Clara.
can go.
Okay, so would you like to go first or second?
I'll go first.
Okay, go ahead. Where do you would like to
I
place
will
your
put
tile?
the X in the middle.
X in the middle. Okay,
Over there.
so you
Yeah.
put X to the middle. So I'm placing O here.
Yeah, and now I'm going to put X in just above, down your O to the
Down
left.
my O. So
Over
here,
there.
you want
Yes.
to place it here?
Yes.
Okay, so you're trying to make 3 in a row here, I see. So I will place my O here.
Yeah, and now I will go with my X in the left side on the bottom.
Left side bottom. Okay,
Yeah.
so I see you're trying to take this diagonal. So I will place my O here.
Oh shit! You just warned me.
Yeah, right? It
Yeah.
turns out that I was able to win this one.
Yeah,
Okay.
yeah. This is why I didn't want to play. Well,
No, it's good. It's good.
you got
Sometimes
it.
we need
Yes,
to
you
see how
got
we
it.
can win this game as well. But
Well, I put it on the right side on the bottom, and you won.
okay, so if you put here, I will place my O here, which will
Yes.
make 3 in a row. Good. But
Yeah.
if you placed that X here, then I would need to place my O here. So I would not be able to attack against that. So you would be able to indeed find a way to secure a draw again in this situation as well, right?
Yeah.
If you've placed the X here. Good. Perfect. So who else wants to play? Let's play one more time. Anyone?
Okay, Bartu, do you want me to play with you?
Okay, yeah, I see Laura unmuting their recorder.
I can play
actually,
if you want, Bart. I can
Okay, yeah.
always-
So
Thank
we
you.
played with Melody. We've played
I
with
was-
Melody 10 times. So
I was
would
waiting.
want to, yeah. Okay, perfect. Let's go. Look at Laura. Would you like to start, or would you want me to start?
I can start.
Laura, you can start. Okay, where
I
do you
can
want to
start.
place your tile first?
D4.
Can you say that again? Sorry.
D4.
D4. Okay.
Yeah, I just
To
think
the
that
center.
this is a good way to direct you.
Okay. Yeah, that's actually a very nice way. Yeah, I like that. So
It's
I'm
like a
placing
battleship,
O
right?
here. Yeah, exactly. Or like chess, you know? Okay, so I place my O here.
Mm-hmm. Okay. All right. E3.
E3. Okay. So I will place my O here.
C4.
C4. Okay. So I will place my O here.
All right. Well, yeah, it's gonna be a tie. Gonna be D5.
D5. So I will place my O here, and this is the only place X is left for. Neither of us got 3 in a row. It was again
tie.
a draw. Good. It was again a tie. So we played this 3 times, and in all those 3 of them, we were able to figure out a strategy. It doesn't matter if we start first or second. We were able to figure out a strategy to make the game end in a draw. Okay, so let me go back to the presentation. So we played this game multiple times, and after just a few moves, the board started feeling familiar. We were able to know what we aim for. The strategy was clear. Try to capture the diagonals, because in the diagonals, you have multiple choices to get 3 in a row. But if you get the centers, not just the center, but to the sides of the centers, you have only 1 or 2 options to get 3 in a row. So that kind of limits you. That's why capturing the diagonals was kind of the main strategy. And whatever we did, we were also able to know how to attack and how to defend, how to block. So that's why our instincts started kicking in almost automatically. And we knew that if both of us, both parties play according to the strategy, it will end in a draw. So now let's break that feeling. Now let's ask the most powerful question in mathematics and in creativity. Let's ask, what if? What if the rules were slightly different? What if the pieces behave differently? Or more importantly, what if the board itself was different? Well, how can we think about this? As you know, mathematicians love coffee. A very famous mathematician said that defined being a mathematician as mathematicians are people who turn coffee into theorems. So let's talk about coffee. Let's talk about coffee mugs, okay? Let's imagine we print this tic-tac-toe grid on a coffee mug. What does it mean? It means that it should wrap around the coffee mug, but there is also a handle. So what are we going to do that? Well, the grid will wrap around the mug, and the left edge will connect somehow with the right edge, because we have this plane and we are connecting the edges together so that we have a cylinder. But having a cylinder is not enough. We need a handle as well. Okay, well, that looks a bit complicated, because here, what does even 3 in a row mean? Do any new winning lines appear? So to understand this, I drew this very ugly looking shape. This shape looks very ugly on purpose. So as you can see, on a coffee mug, it didn't help us a lot. But as mathematicians, as I said, we love coffee. What else goes good with coffee? A donut. So instead of a coffee mug, why don't we print this grid on a donut? Now, imagine the top edge also connects with the bottom edge. So consider this. You connect bottom with top like this. So you have a cylinder, and then you rotate the cylinder and connect the left edge with the right edge. So what you end up with will have a hole in it, and it will be like a donut. So mathematicians call this shape a torus. And also, we call it as a donut surface. Here, our tic-tac-toe grip will wrap in both directions at once. And if we draw it like this, the left is connected with right, and top is connected with bottom. So right now, let's ask the same question. Can we win in any new ways? Or if our old instincts about rows and columns will stay valid or not? Well, we may think, Bartu, it's still like a surface. Even though it isn't flat, it's still a surface, so it should not be that much of a difference. Well, make this observation. Let's start with this bottom left corner. Now, observe that we identify left with right. So what does it mean? Since left is identified with right, bottom left corner is identified with bottom right corner. So that means they are not 2 different corners anymore. Those corners are identified together. They're glued. So they are the same corners. All right. What else? Well, top is also identified with bottom. So that means bottom left is identified with top left. So that means those 2 corners are also not different. Similarly, bottom right is identified with top right. So they are not also different corners. So here, we don't have any 4 different corners anymore. We have all of them identified with each other together. So this shape looks like as if we have only one single corner in it. How surprising it is. So that means that when you place an X here, you are placing an X kind of to the top of this top corner, because this corner is identified with here. So if you continue going down, 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 if you continue going down, you are back here. You continue going down indefinitely. So that means that it is as if you are expanding the tile. When you put an X here, it is as if you put an X here, or it is as if you put an X here. So I know that this might feel a bit confusing and unexpected completely. That is why I prepared this other Excel tile, where we play on a torus this time.
Yes,
Well, we
and then we
play
want to emphasize that even though it looks like a flat surface right now, always think that it's a donut. So just
Yeah.
like remember what Bartu made. Yeah, that's the trick.
Exactly. So we always wrap it around. So for example, when you place an X here, this X is also appearing here, because this side is identified with this side. Left is identified with right. Similarly, top is identified with bottom. So that X appears here. Or if you place an O here, it appears here as well, because bottom is also top. As you can see, the board changed significantly. So now, in this board, who wants to play against me? Maybe we can start playing with Melody. What do you think, Melody? Yeah?
Okay.
Okay. Good.
Okay.
So
Can I start?
you can start.
Okay, so let me see. I would like to put an X on the middle left.
Middle left.
An X, please.
All right, the X appears here as well. So I will place an O here.
Now I would like to place X under my first X.
Under your first X. Okay. So there you are. So you are about to make 3 in a row. So I will place my O here. When I place my O here, it appears here as well.
Oh, then I
Okay.
can only put my X in between, in the middle of your O's. You don't give me
Here.
another chance.
Yeah, so
Yes.
you put an X here. Good. So
Okay.
what am I gonna do now?
This is
So
more
let me,
fun than traditional tic-tac-toe.
yeah, so let me place my O here.
Where?
To the center.
Oh, you've already put, sorry, I missed it.
Yeah.
All right. Now, if I put my X here, it's not gonna work. Oh, it may work. I can put my X here. I have a feeling that I should put it like middle down, like under your O.
Here.
Yeah.
Okay. But then I can place my O here, and then it will give 3 in a row.
Oh, I lost it.
Yeah. Yeah. So, as you can see, we have tons of different strategies now. And indeed, the board is completely different now. You can play it in a completely different strategy. And indeed, here, draw is not always a conclusion, an automatic conclusion. I can see Amber raising their hand. So, yes, go ahead, Amber.
I think I conceptually get this, but I just want to like make sure I understand the rules of the game when it's a donut. So like when you guys were playing in the blue and the orange spaces, those were also like playable fields. So if you would have gotten 3 across in those would have also counted.
It will count, exactly. So if you place your X here, and then here, it makes a diagonal, as you can see. Because that X
like
appears here, that X also appears here. So this is a very valid win. Even though inside the...
Sorry, that was a very valid question because we changed things and Amber wanted to clarify the rules.
Exactly. Thank you very much. That was actually a very nice question. And yes, that is true. So here, inside the grid, it looks like you don't have three in a row, right?
Mm.
But actually, you do have three in a row as a diagonal. But here, you don't see it when you just look at the grid. You need to look where it's wrapping around, because
You
your
have
X
four in
here
a row
also
here.
appears here.
So you have four in a
You
row?
also, yes, kind of, but you place three X's, but some X's appear in multiple different places. For example, this X impacts here and also here. Or this X impacts itself and also this place because it wraps around. So you don't copy that X, but that X has more directions to go because you wrapped it now. You wrapped it around. That's the only reason. You didn't actually change the flatness of the surface. You just wrapped it. And it completely changed how the game can be winnable now. And indeed, you can prove that there is a always winning strategy for the person who starts the first. So now, what just happened to our brain? The old strategies stopped working. We had to adapt our thinking to a new context. We had to decide what to keep and what to change. We had to select what things are important. And we had to invent new strategies from scratch. And this is what exactly mathematicians do. And it's called mathematical creativity. So Melody will take from now.
Okay, so we all know what creativity is because we are studying creativity, we are a part of it. But how exactly math creativity is different than the creativity we know? So that's an important question because there's a distinction. So as you can see here, we played a traditional game in an unconventional way, and we used our creativity skills indeed when we were playing the game. And when I say creativity skills, like the first couple skills that comes into our minds is like, oh, we know that making associations, thinking by analogy, we are generating many different possibilities. So these are the things that we are familiar, and these are called domain general creativity skills. But then how is math or domain specific creativity skills? So if you think of that way, a poet, a scientist, a designer, and a mathematician actually use the same skills. They are not like different skills, but they use it in a different way depending on their purposes. For example, here when we were playing the game in the new surface, it was more about adapting to the change in the surface because the first tic-tac-toe was played on a Euclidean plane like a flat grid, but the second one was a torus, a donut shaped surface, which actually is non-Euclidean mathematics, right? So here there was a change in the board we were playing, and now we tried to adapt the change. And here what we did actually is called selective encoding, meaning that we decided to see the separation of relevant from irrelevant information in regards to the change in the field, in the plane we are playing. And we try to select one of the most fitted mathematical solutions in this game. It is the strategy that you chose to play with. So this is how you apply the domain general creativity skill in a domain specific context. What else also we did, we became flexible. So to be able to adapt to the new situations, we had to change our perspective. And it is really difficult to do so without understanding the dynamics of the game and the features of the new surface, which is a more circular topological surface. Can we skip to the next one? Sorry, not the 10th one. Okay, we can stay there. So therefore, what I'm trying to say that mathematical creativity emerges when general creative processes are shaped by mathematical structure, constrained by logical rules, in this game, the rules of the game, plus mathematical rules, like how does a surface look in a Euclidean geometry or non-Euclidean geometry. And in mathematical creativity, creative processes are expressed through mathematical language and concepts, because Bartu was trying to tell you how the surface would look like if we kind of bend the field, So these all required some sort of mathematical language. So couldn't you play the game without knowing these things? Yes, but wouldn't it make it better if you knew or had a better understanding of the surface? Yes, so that's kind of the sweet spot between domain general creativity and domain specific creativity. And then, yes, 11 is good, thank you. And now if we
Melody,
go,
we have a
yes.
question from Clara. What is torus? Okay, you was just explaining it's different from Euclidean, right? What is torus?
Torus is this
It's donut shape.
You can see it on the right bottom part of the slide, Clara.
Yeah.
This is how a torus looks like. Yeah.
Yes,
Yeah.
thanks for the question. So it's a donut shaped math language is torus. Okay.
Okay. So is that cylindrical donut shape is in mathematical language called torus, correct?
Torus.
That's
Exactly.
true.
Yes, great question. Thank you. The top image, Amber, is actually Mobius stripped, and I'm gonna come there very soon. That's another, again, non-Euclidean shape. We're gonna come there because that also changed the strategy if you want to play a tic-tac-toe in that type of field. So this is the main
Yeah.
idea. I love the questions because once you start to ask what if questions, then it never stops. It never ends. Okay, how about this shape? How about this field? So that's kind of goes like this. But if we go back to our experience with the new tic-tac-toe, like enhanced version of tic-tac-toe, what we did actually, how we embodied creativity skills. First of all, we were overall creative because you were inventing new versions of a familiar idea. We know that, it's just improvement of existing ideas is a big creativity thing. And then Bartu was created because he invented a new game when he decided to move the tic-tac-toe to Taurus. When you were playing, you were flexible by adapting when the context shifts, because you realized that your old strategy stopped working. And then Amber was asking questions because she was trying to clarify the new rules, which was a great attempt actually. So because it was attempt to adjust, making some changes, and you were in the exploratory mode. So that's very important. This stays same, whether it is domain specific or domain general. If you are open-minded and if you are in a playful mood, that's also the attitude that helps us be creative. Also, we were selective, meaning that we were deciding what to keep, change, or drop when we carried our game from a flat grid to a donut shaped surface. So, and then you had to ask yourself, for example, in the original tic-tac-toe, a diagonal count as a win, but does it still count as a win on a donut-shaped surface? So you had to stretch your thinking and you had to be explorative. And now, Amber, to your question, you can even ask more what if questions, and you can say, what if we played this on a Mobius strip, the top shape on the top right end. So Mobius strip is actually think about of a paper. Bart, do you want to show it? Like, yeah.
Yeah.
Can you
So think of a
demonstrate?
piece of paper.
Yes, and then you
Instead of
flip.
identifying the edges from top to bottom like this, you rotate one of them, you bend and then identify. You rotate and then identify the edges. So it looks something like this.
And
It looks something like this.
yeah, the top right shape is actually how it looks like.
Yeah.
So now,
So
because
instead of connecting automatically, you connect by bending.
exactly, and that changes everything. Again, think about this. The first tic-tac-toe was on a flat grid, and then we moved it in a donut shape. We moved it in a non-Euclidean geometrical like realm, and then the other one, the Mobius strip, it's still in the non-Euclidean geometrical realm, but the rules still changed because now we changed the way that we fold or flip the paper, right? So because we flipped it in a way, then the orientation changed overall. So as
Exactly.
a result, what we think of as a diagonal here in this Mobius strip would transform into almost a vertical V-shaped line. Now you wouldn't be able to have a diagonal like kind of order, so it was gonna end up like a V-shape line. So, but I know that's a little bit of a stretch for people who are not familiar with the non-Euclidean geometry, but we are trying to say that just by asking what if questions and just by applying domain general creativity skills to a math context and concept, you can still be creative. That was my point. And actually, it's important to study math creativity. And you could ask us, like, okay, like we didn't learn math in a creative way. It wasn't never taught us something like this, because unfortunately in traditional math education system, there's usually math is taught as a sequence of procedures like theorem, proof, example, repeat, drill, and practice. So they don't necessarily have students or people enjoy the fun part of it, because this is the fun part. And as you experience, you don't necessarily need to know torus or the details about it. You just need to understand the change and then change your thinking or logic in regards to this change in the field. So it's not about like knowing the concept of torus, it's more about understanding this new change. And actually, we know that in this era, creativity is one of the top 10 skills that employers seek out of their employees. And then we know that even though you know about domain general skills, if you don't know how to transfer those skills to the content, to the context that you're studying, it's a little bit challenging. You need more guidance. So we thought that we should increase the attempts for people to experience math creativity. And indeed, we did a study about it, and we published a paper about it, because we wanted to see if we deliberately, intentionally teach how you can be creative in mathematics. We wanted to see if it is really gonna improve our participants' creativity in math. And actually it did, because we had couple indicators of math creativity, like making associations, using a lot of representatives, being divergent, and this and that. And actually throughout a couple of weeks, even in that short period of time, students' creativity skills in math increased. And on top of that, they were more motivated to do math. So that math anxiety is a big thing. And actually, Bartu and I think that it's not about math is difficult. It's just what we teach in the classrooms is actually not what mathematicians do. And mathematicians are indeed very, very creative. So, and then speaking of mathematicians, I again hand it to Bartu. So he talks about a very famous mathematician who invented this non-Euclidean field.
All right. Thank you very much, Melody. So we will now wrap up with a little topology, which is a study of shapes, but special sort of shapes in mathematics. So I'm going to start with a brief story. The year is 1736. In a city called Königsberg, which happens to be the capital of East Prussia back in those times, a beautiful city. There are 7 bridges, there's 1 river, and there are 2 islands on it. And there is a puzzle everyone in town argued about. It was actually about postal men using every bridge only once and only once, to distribute all the posts in the most efficient way. The puzzle is, can you walk through the city crossing each bridge exactly once? People tried and failed. But nobody also was able to show that it was impossible too. So they were confused. But then a Swiss mathematician, an extremely famous mathematician, Leonard Euler, looked at this map differently, where you have 2 big lands, and there's a river in between, and there are 2 islands, and these are the 7 bridges connecting those. So Euler said this: stop thinking about streets and distances. All that matters is which land masses connect to which lands. Apologies.
Bless you.
Okay, so all that matters is which land masses connect to which lands. So he replaced the map with a simple diagram of connections. Then he proved crossing each breach exactly once is impossible. So he stated actually a very big theorem. He showed that you need to only count for every node the number of connections. If every node has an odd number of edges, there cannot be such a walk that passes through one bridge exactly once. Indeed, he proved that the number of odd number connections should be precisely two. But long story short, the main outcome, the main upshot that we can take from this is Euler did not solve this puzzle by working harder. He solved it by changing the question, changing his mindset and his point of view. He asked, what is the essential structure here, stripped of all extras? He asked, and he observed, the length doesn't matter. The corners doesn't matter. The only thing is whether a connection exists or not, whether you can make a loop or not. Only those questions were valid questions from his point of view. So that was the birth of graph theory and also topology. And topology is the mathematical study of shapes, connections, and holes independent of distances and angles. So that is why for mathematicians, for topologists, a coffee mug is the same thing as a donut because both of them share one hole. We do not care about distances, we do not care about corners, we do not care about angles. All we care about is if we can continuously shrink shapes to each other or generate shapes in a bigger way. So as I said, we do not care about how big or round something is. We ask how they are connected. That's why a coffee mug and donut are same shapes for a topologist. Similarly, a sphere and cube are same shapes because both of them do not have any holes. Okay, so back to Melody to wrap up now.
Yeah, so it was actually Euler's creativity as a mathematician. So that's very important because mathematicians, if you're a real mathematician, you are creative, especially if you are working, studying on ill-defined problems. Okay, so Euler was a creative as mathematician because he invented a new diagram to represent a real life problem crossing the bridges in real and existing city, which was actually a great example of mathematical modeling. Mathematics really tries to kind of represent the reality in its own with its own like information and concepts and rules. So he was creative because he invented a new diagram. He was creative, he was flexible because he let go the idea of distances, angles, and coordinates, which was dominating mathematics and geometry back in then. And he decided to keep only connections, just like we do in Scamper in the elimination part. Sometimes we just strip all the extras and we focus like what's my main point here. So that was very flexible of him. And he was also very selective because he decided the number of bridges at each point was all that mattered if he wanted to solve the problem. So actually, these are the same things you used when you were trying to adapt to the change in the tic-tac-toe board. So what we want you to understand that whenever you are in your playful mood, whenever you are explorative in mathematics, actually you are no different than in a mathematician. Okay, the only difference is that they have more information, but it is not the main idea. Even though you may have more information, doesn't necessarily guarantee that you are going to be creative. So Bartu, can we jump to the 21, please?
Sure.
Thank you. So overall, what we did today, so we played a game, we had fun, although it was a challenging one, you know. So, but we played a familiar game, then we played it in an unfamiliar way. We asked what if questions and what would happen to our tic-tac-toe game if we asked what if questions, what if the board was different? That was the main question. Then it generated like rules were different, what if the pieces behave different? And we discovered that a game can live on many surfaces And we saw earlier using the same kind of thinking 300 years ago. So we should be proud of ourselves, because we kind of led the same path that Euler took. And can we go to the 23rd form, 23, please? Oh, here, yeah. And while we were doing it, we didn't use any formulas. We didn't use any advanced terminology rather than torus. And we saw that we could even say donut. It doesn't matter. We just played, wondered, used our imagination and followed the question wherever it led. And actually, this is what mathematical thinking feels like from the inside. So one small what if question can open a whole world, a whole new world of possibilities. And like we saw that this is kind of how domain specific creativity is different from domain general creativity. Thank you very much for joining us, for playing with us, and for listening to us, even though the concept was not familiar to you. We
Yeah, thank you
appreciate
very much. And also here's the QR code to our paper on mathematical creativity and education and different instruction methods. If you folks are interested, you can scan the QR code and access the paper. Thank you.
Can I ask a question? I am just kind
Absolutely.
of like my brain is spinning right now. So
Absolutely.
in terms of how fascinating I found this presentation, just because we grow up with the idea that mathematics is just one thing and it's very Euclidean, right? That's
Yeah.
what we do. I associate I'm a philosopher also as well. So this for me is it is really like getting into, so that's my background as a philosopher.
Mhm.
And so really thinking about Euclidean and the shift and the paradigm shift, right? So
Mhm.
I mean, the question for me is, what is one practical example of application of mathematical creativity? So I understand the pedagogical, so the education, so we should teach mathematics in a different way to kids. But if I
Mhm.
think about the world of innovation or creativity, where mathematicians actually play a role in some
Mhm.
big breakthrough in creativity, do you guys have any example
Yeah, for
of
example,
that?
Bart, we can talk about like how we model the viruses, how they spread. Can you talk a bit about mathematical modeling?
Absolutely. So, like for example, consider during COVID times, we had a
Mm-hmm.
very limited amount of testing, right? So a big question was, how can we come up with the most efficient way of testing by using the least amount of tests possible?
Mm-hmm.
And if you test, you can test everyone one by one, and you can find how many positive and negative cases you have, of course. But you don't want to test everyone one by one. It is too many samples. You need to test everyone in the population. Here in the US, it is more than 300 million. So, and you don't have those resources. So you ask as a mathematician, well, how can I reformulate this question in a different way? Because it's like kind of like a grouping game. So why don't I group people in half, put one half of the entire population in one sample, the other half as another sample? I use only two samples, but if there is only one person who is infected, by only using two tests, I know in which half that person is. And then I can select that half. I can continue doing that until I get that person. And by using the power of exponentiation and exponential growth, you can indeed find the person who is infected by using 20 tests at most. Because 2 to the power 20 is a huge number, much bigger than 300 million. So that is kind of an example how when we start shifting how we look at the question by not just using mathematics, but also using different methods. And also this, for example, this idea, the idea that I just described to you, has been theoretically discussed since 1960s. And now it is actually a mathematical concept that there are books written on it. How to group select out of a given sample size. How to use our resources in the most efficient way, kind of. So that was only one single example. Wherever you look at, you use this similar optimization ideas, which stemmed from asking well, how can we change this kind of mind shift?
Thank you,
Yeah.
Bartu. This is a very concrete and very useful example for me. Clara, you have a question or something as we are wrapping up here?
Well, yeah, for me, this was a fantastic session.
It's amazing.
Thank you.
It's fantastic. Since I was very little, I know that I'm dyslexia with numbers. Okay.
Mhm.
For instance, for Laura now is 2 o'clock. For me it's 12. I cannot understand why she cannot tell me what is going to happen to me when it's my 2 o'clock. This is something that is not in my mind, and I have never been able to understand.
Mhm.
When you put
Mhm.
this in a spatial way, for me it was totally clear.
Wow.
I mean,
Wonderful.
there was something so different in the donut shape that immediately I had a sense of what was happening. That when it was in a complete straight, I was not able really to win the game, and I have never been able to win it. You see,
Mhm.
so I think that this goes beyond what is mathematical thinking. It is a way also for training or developing people that are not good with numbers. No, I appreciate this very much. For me, it was a huge aha, and I thank you very much for this. Yeah.
Thank you very much. We very much appreciate your. We're very happy to hear that.
It gave me an idea actually, Bart, that we can actually study with people who have ADD and then some number like that, like what dyscalculia, you know, so that could be an interesting study indeed. So Clara,
Absolutely. Yeah.
Yeah. And for me, I wanted to say, to underscore, I mean, it was mind blowing, really. Thank you so much. I didn't know what I was walking into, but I had to be here as I was moderating, and I'm so thankful about that.
Yeah.
Yeah, for me, and I can see all the educational, right, application of
Mhm.
it, but I can also see, so because I have always had a strong clarifier preference, right? You know, in for
Yeah.
side terms, like, and that's part of. I mean, it's really style and preference from birth. Why did I choose to be a philosopher or to study philosophy? Because the
Mhm.
question is the most important thing.
Yeah.
Is about the question.
Yeah.
And the question is what comes out of this presentation that you guys had. It is about the question. You change the question, and we know, like, you know, we have a quote from Einstein, right? You know, and all of that about how that change of the question, that reframing of the question, they're looking is
Mhm.
really where the breakthrough, the creative breakthrough is. I mean, I'm not discounting the ideation, I'm not discounting the many ideas that will come at that, but that shift of paradigm, and one of my passion when I was studying philosophy was philosophy of science. So I went to all, like, you know, Thomas Kuhn, all the kind of paradigm and science
Absolutely.
kind of thing. So it's just the implication of this work for me are really so fascinating, and I think you guys should spread that more.
Thank you very much. Thank you very much for those kind words and also very constructive feedback for us as well. Thanks a lot.
Yeah, so thank you. And Clara, it was a pleasure to see you. We still have some people here, and Michelle, Lakshmi, we are closing our conference actually right now, and
Mhm.
it was great. Like, you know, I hope, like, you know, you had all a great time. And Melody, I will see you tonight in person.
yes, I
All
will see you
right?
tonight. Thanks for
Yeah.
everyone.
Thank you very much, everyone. Bye.
Okay, all right.